Hello guys, welcome back to my YouTube channel, Odavig Structure Hub. This is the #1 channel for structural insight. Today I want to continue from where I left in our previous session. And if you can remember, in our previous session, we tackled design of continuous T-beam, and we only dealt with bending alone. So today I want to continue with shear and deflection. So as you can remember, this was our floor slab plan. I told you I will maintain this until I finish this question. So we designed an L-beam, which was 3A, 3D. So this was the beam. This was the beam. As you can see, it was a continuous beam supporting this side, half of this side, and a half of this side. So for today, I want to continue by solving shear and deflection. And this information you can see on the whiteboard is the information I have picked from the previous calculation so that it can help us in solving shear and deflection. Remember, in our previous section, we had a table that helped us to determine bending moment and shear force for various support and spans. So this table is table 3.5 from BS 8110, and if I can show you the table, so that is the table. As you can see, we have position, bending moment, and the shear force. So for support 3A, and 3A is the same as 3D. So those are the end support. So the bending moment for support 3A and 3D, which is the same, is 0. And then shear force, as you can see, shear force is this one. So if you check in the previous question, you will see this information. So near middle of 3A and B, 3AB, that is end span. So end span, this is the bending moment, and this is the shear force. So the table continues up to middle of 3BC, middle of 3BC. So this is the bending moment, and this is the shear force. So this information is from that table. So in this table 3.5, for you to use such a table, there is some condition which is stated in clause 3.4.3. I think you have that condition. The condition for you to use such a table to obtain design moment and shear force is, number one, the GK must be greater than QK. So the GK, it means the dead load, and the QK is the imposed load. So condition number two, the load should be substantially uniformly distributed over 3 or more span. So this is self-explanatory. As you can see, you have more than 3 span, 1, 2, 3. Then the last one, span are of equal length. So span are of equal length, as you can see, 8.5, 8.5, 8.5. So that one, if that question meets this condition, then you can use table 3.5 of BS81 to obtain the shear force and design moment for such a continuous T-beam. But if it doesn't meet this condition, it means you will solve or you will analyze first the continuous beam using one of the advanced method of continuous beam analysis. Example, moment distribution method. Number 2, three-moment theorem. Number 3, slope deflection method, such that you will come up with the maximum bending moment and the shear force, and then you plot the diagram for bending moment and shear force, indicating critical values. And then from there, you can be able to design such a beam. So let's continue. This information is what is on the far column. So I will erase this and keep this for proceeding calculation. So I want to begin by span 3AB. So we begin by shear. So span 3A, B, 3B, C. And 3CD. So this is span 3AB. So this is 3A. B is here. So this span from here to here. And then 3B. So this is 3B, C. This span from here to here. And then span 3C, D. So this is 3C, D, this span. So 3 span, 1, 2, 3. Now we want to design the shear reinforcement in this span. The shear reinforcement in these 3 span. So here, this span, this, and this. So if you check in section, section 3.9.1.3 of BS 8110. So in this section, it says that the amount and the spacing of reinforcement depend on the area of tensile steel. Reinforcement present in the beam. So in our beam, the minimum tension still at any point in the span is, so the minimum tension still at any point in the span is 2y25, and the area is equal to 980 millimeter square. So if you check in the design of in the design for bending, for all supports and a span, you will see this minimum tension steel, so which is 2y 25, and the area given is 980 millimeter square. So we want to use this area to determine the shear stress in concrete. And you know that to determine the shear stress in concrete, you will need this formula: 100 AS over BB. So this one is equal to 100 area of steel is 980 over B. You remember our B was 300 times D. So for D, we also calculated the value of D in our previous example or session. And if you can remember, for span, for the end span, our D was 499. So 499, this was our D. So this one, if you punch the calculator, you will get 0.655 or 0.66. So that is the value if you punch this in your calculator. So after obtaining this value, 0.66, you will proceed to table 3.8 of BS 110, such that you can obtain your VC. So in this table, I will show you the table. In this table, as you can see, that is the table. So this table, it has 100, the value of 100 S over BD, and then the effective depth. So you will come with your value, which is 0.66. So as you can see, there is no 0.66. So you will choose a value which is lower than 0.66 and slightly higher than 0.66. So this is 0.50 and 0.75. And then we proceed to the effective depth, which is, as you can see, we have greater than or equal to 400. So you will come to that column, and then the value corresponding to 0.5 is 0.50, and the one corresponding to 0.75 is 0.57. So we have obtained the value for 0.50. So this one is 0.50. And then at the middle, you have 0.66. You don't know the value for 0.66. And 0.75. The value here is 0.57. So you will interpolate this one so that you can obtain the value corresponding to 0.66. So this is how you will do it. So take this one, take 0.7 minus 0.50. So 0.75 minus 0.50 over 0.57 minus 0.50 is equal to, come to this one and get the difference. So 0.66 minus 0.50, then over this one, say this is x, so here it will be so over x. Then you will find the value of x, whereby which imply x is equal to 0.04. So to get VC is equal to, you'll take 0.04 plus 0.50. So this one is equal to 0.54 Newton per millimeter square. So that is our VC for class 25, but not class 35. So our question, it has a class of 35. And you can remember that the VC given in table 3.5, it only applies for class 25. So VC given in table 25 only applies for VC given in table 3.8 only applies for class 25 of concrete. So for you to get VC for other classes, so you take, for example, for this case, our class is 35, so you'll take 35 over 25 raised power a third times 0.54. So VC is equal to So VC is equal to 0.60 Newton per millimeter square. So that is VC for class 35. So I think in the previous examples, that is for singly and doubly, I made a small mistake for calculation of VC. So I skipped this part because the VC given in table 3.8 only applies for class 25 of concrete. For any other classes, you always take the class given in the question over 25 raised power a third times the value obtained in table 3.8, for example, 0.54, and you will get your VC. So I'm sorry for that. It was a small mistake. and I think you can correct it. Now you will provide minimum link, provide minimum links where V is less or equal to VC plus 0.4. So our VC is 0.60. So use this equation to obtain minimum link where V is less or equal to VC plus 0.4. So this is ASV over SV is equal to 0.4 B over 0.87 FYV. So our V here, so let's proceed. So ASV over SV is equal to 0.4 times B, which is 300, over 0.87. FYV is 460. So this one is equal to 0.300. So ASV over SV is equal to 0.300. With SV is the spacing of the link, and ASV is the area of the shear, is the area of the shear steel. So with SV less or equal to 0.75 D, so 0.75 D, which is 499, is equal to 374 millimeter. So you will use this figure, you will use this 0.30 to obtain the size of the shear reinforcement bar and the spacing of the shear reinforcement. And remember, it should be equal to, the spacing should be equal to 374 millimeter, less or equal to 374 millimeter. So let's proceed to table 3.13. So table 3.13. So select Y8 at 300 millimeter center to center. And then ASV over SV is equal to 0.335. So I will show you how to obtain this from the table. So this is table 3.13 of BS 8110. So our value there is 0.30. So you will go for a value that is slightly higher than that. So This is the diameter and this is the spacing. So you have selected Y8. This is Y8 and the spacing is 300. Spacing is 300. So this is the spacing and then 0.335. So that is how you read it from the table. Now we have calculated the minimum links for this span 3AB, 3BC, and 3CD. We now proceed to the support. We now proceed to the support 3A, this support, and support 3D. So support 3A and 3B. So these are the end supports, support 3A and 3D. So according to clause 3.4.5.10, for beams carrying generally uniform load the critical section So according to clause 3.4.5.10, beams carrying generally uniform load, the critical section for shear may be taken at distance D beyond the face of the support. So for example, i.e., in our case, we have this support 3A and support 3D, which are the same. So the end support. So for this, we will take a half of this support. Remember the question, we were told the column is 200 by 200 millimeter, no, 400 by 400 millimeter. So for the critical section for this column will be a half, will be 400, a half of 400 plus D. So this one is equal to 200 plus D, which is 499. So this one is equal to 699 millimeter. So according to clause 3.4.5.10, so this one will be the critical section for shear. Now, having obtained this distance for critical shear from the column center line, we now calculate the design shear force VD. So design shear force for VD. This is capital V. So it means if this is the support, and this is the loading on the beam, and the D is somewhere, let's assume D is here. So this is D, and this is the support. So if we know the shear force at this support, which is this is support 3A or 3D, support 3A and 3D, which is the same. So if you can check on this side, we have the shear force for support 3A and 3D, which is 209. So here we have 209.6 kilonewton. And remember, our loading on this beam, as we calculated earlier or in our previous session, it was 54.8. So now we want to calculate the design shear force at this point, at D, the reaction at D. So how are we going to calculate the reaction at D? And remember, the distance between these two supports is 0.66. So 699 you divide by 1,000, you'll get 0.699. So let's make it 0.7 meters. So for us to obtain the shear force at D, or reaction at D, so we will start summing our reaction from this point. Whereby we will have 209.6 minus 54 times 0.7. So this one will give us reaction at D. Because this one is in the downward direction, it is a minus. So if you carry out the operation, the VD or RD, this is capital V, is equal to 171.3 kilonewton. So that is our VD. So we will use this VD to calculate the shear stress, which is small v, at D. So V, small v, which is the shear stress at D. So V D is equal to V over B D. So this one is equal to 171.3 times 10 raised to the power 3 over B, which is 300, times D, which is 499. So you will get 1.14 Newton per millimeter square. So that is our shear stress at critical point, which is D. Now, after obtaining this 1.14 Newton per millimeter square, we proceed to the VC, the shear stress in concrete. But before that, I want to talk about curtailment. So we will say 50% of main bars or steel is curtailed at support A. At support A, so the effective area of tension still is the effective area of tension still is 2y25, then area is equal to 980 millimeter square. So what is curtailment? So curtailment, it refers to curtailment is the shortening the length of reinforcement bars in a structural element based on design calculation where the bending moment or shear force is lower and full reinforcement is not needed. For example, if we have a simply supported beam, like that, you know that this beam will bend in such a manner so that is how this beam will bend. So where the maximum deflection will be at this point X. So X is where we'll have the maximum deflection. And at supports, let's say support A and B. So at support A, the deflection will be 0, which is equal to B. So for such a case, when you are designing or when you are designing the reinforcement for this beam, there is no need for a reinforcement, for 100% reinforcement to start from this support to this support. The reason is the bending moment at support are 0. So you can curtail. You can do the curtailment at this support, maybe to a place somewhere like there. So this is why you will provide curtailment for some reinforcement. So let's say 50% curtailed and also 50% curtailed, because there is no need for 100% of this reinforcement to reach at the support. And here is we will have 100% reinforcement bar passing between this point, because this is where we will have the maximum bending. So that is all about curtailment, and I will talk about curtailment at the end of beam design, that is a singly reinforced beam design. doubly reinforced beam design and continuous beam. So I'll provide the information for at the end of this topic of beam design before I begin slab design. Now, the shear stress in concrete will be obtained using this formula, 100 AS over the D. So this is 100 times 980 over B, which is 300, times D. Our D is 499. So this one is equal to 0.655. So if you round it, you will get 0.6 Newton per millimeter square. So that is our VC. Now this one is equal to 0.66. If you round it, it's equal to 0.66 Newton per millimeter square. And remember, this one is for class 25. No, you will go to the table. You will again go to the table to obtain VC for class 25. So this is table 3.11. But since this is the same thing we have done for this span, so there is no need to repeat ourselves. So our VC, small VC, for class 35 of concrete is equal to 0.60 Newton per millimeter square. Remember, we have already done the similar thing in this span 3A, 3AB, 3BC, and 3CD. So no need to repeat ourselves. Now, since V, which is 1.14, this one, Newton per millimeter square, is greater than VC, which is 0.6 plus 0.4. So this is 0.60 plus 0.4. It will be 1.0 Newton per millimeter square. Since V is greater than VC, therefore provide design links according to ASV over SV is greater or equal to V minus VC over 0.87 FYV. So this one is equal to B is 300, and then V is 1.14 minus VC 0.6 over 0.87 times 460. Yes, times 460. So this one is equal to, if you punch this in your calculator, you will get 0.405. 0.405. So from the table, now from table, this one should be on this column. This is table 3.13. So select Y8 at 225 millimeter center to center. Then ASV over SV is equal to 0.447. I hope you know how to read this table 3.18. So let me show you. That is table 3.13. So this is 8, Y8, and then 0.447. We now proceed to support 3BA and support 3CD. So this support. So support 3BA and 3CD. So design shear force at distance D beyond the face of support So remember, this is clause 3.4.5.10 of BS81. So this one is equal to 0.2, or a half of the size of the column, which is 0.4 over 2, then plus D, which is 0.487. So the D changes. Remember, our D for support 3BA, this is the support 3BA, and 3CD. In our previous calculation, it was 0.487 meters or 487 millimeter. So this one will be equal to 0.687 meters. So VD, which is the shear force at D, which is critical, shear force at D is equal to, so again you can draw this beam. So this is 3B, so 3BA, and this is D. And this is 54.8, and the distance is 0.687. So to obtain the shear force at D, which is critical, remember we are moving from 3BA, so this is 3B, we are moving to this side, 3BA. So our D is somewhere here, let's say somewhere there. So we want to know the shear force at this point D. So, but you know the shear force at 3B, which is 279. So here it is 279.5 kilonewton. So VD is equal to, remember it's capital V, VD is equal to 279.5 minus 54.8 times 0.687. So this one is equal to 241.9 kilonewton. Then the shear stress V is equal to V over BD. So that is 241.9 times 10 raised to the power 3 over B, which is 300, times D, 487. So this one is equal to 1.66 Newton per millimeter square. Now, the steel, tension steel is equal to 6y25, then area of steel is equal to 28.37 millimeter square. So remember, we designed this support 3B and 3C in our previous session, and the reinforcement for steel, it was 6y25 and the area 28.37 millimeter square. So for us to obtain the VC, which is the shear stress in concrete, we always use this formula, 100 S over BD. So this one is equal to 100 times 2837 over 300 times 487. So this one is equal to 1.94. And then you proceed to table. This is table 3.11. So in this table, I think at this juncture, you know how to read this table and do the interpolation. So we have 1.50 corresponding to 0.72, and then 1.94 corresponding to, we don't know the value, we call it x, and then 2.00 corresponding to 0.80. And then you do the interpolation so that you can find the value of x. I think you know how to read this from the table. There's no need to keep on repeating what you know. So to save time, do it on your own. So then you can interpolate to find the value of x. So get the difference between these two. Also the difference between these two. The difference between these two. So to obtain x, it will be 2.00 minus 1.50, as I have said, over 0.80 minus 0.72 is equal to 1.94 minus 1.50 all over x, which imply x is equal to 0.07. So the VC, small VC, which is the shear stress in concrete, is equal to 0.72 plus 0.07. So this one is equal to 0.79 Newton per millimeter square. Remember, this is for class 25 of concrete. To obtain class 35 is equal to 35 over 25 raised to power third times 0.79. So this one is equal to 0.88 Newton per millimeter square. So this is our VC in concrete. Then since V is greater than VC, our V we calculated is, our V is 1.66. So this is 1.66 is greater than VC plus 0.4, not just VC. So this is V is greater than VC plus 0.4, like that. So this is 1.66 is greater than 0.88 plus 0.4, which is 1.28 Newton per millimeter square. So now you will design link. You will design link according to, so design link according to design link according to ASV over SV is greater or equal to B V minus VC over 0.87 Fy V. So this one is equal to 300 over V, which is 1.66, minus VC 0.88 over 0.87 times 460. So this one is equal to 0.583. So this is SV over SV, like that. Then from table, select, this is table 3.13, select Y8 at 150 millimeter center to center. ASV over SV is equal to 0.671. So it should be higher than this, slightly higher than this. So I think you know how to read this, the size of the bar and the spacing from table 3.13. So that is all about support 3BA and 3CB. We proceed to support 3BC. Support 3BC. Support 3BC and 3CB. So this is support 3BC. This is 3BC and 3CB. So we are moving in this direction from here. We move in this direction from here. We move in that direction. So shear force at distance D from 3BC is shear force, which is capital V, at distance B from support 3BC, which is VD, is so remember our critical distance is 400 over 2 plus 487. So this one is equal to 687 millimeter or 0.687 meter, just the way we did in support 3BA and 3CD. So that is our critical distance for shear. Now, we now proceed to this shear force V at distance D from support 3B is, this one is given by, you can also draw this. So this is support 3C. No, this is support 3C, and this is D. And the distance is 0.687. Then you have the loading, which is 0.54. And here at 3C, we have the V, which is 256.2 kilonewton. So it will be easy to obtain the shear force at D. So at D is going to be 256.2 minus 0.54 times 0.687, like that. So this one is going to be 218.6 kilonewton. So this is our shear force at critical point B, which is away from 3C at a distance of 687 millimeter or 0.687 meters. So our shear stress, which is V at D, is equal to V over BD. So V is 218.6 times 10 raised to power 3 over B 300 times 487. So this one is equal to 1.50 Newton per millimeter square. So the tension still is 6y25. The area of steel is equal to 28.7 millimeter square. Like that. So let's proceed. So this formula 100 S over BD will give us a value that will enable us to enter into table, which will give us a VC. So this one is equal to 100 times 28.7 over 300 times D 487. So this one is equal to 1.94, not Newton. There is no unit for this. So 1.94. Then our VC, this is the same calculation we have done for a support 3BA and 3CD. So there is no need to repeat ourselves. So we'll just skip some calculation here and proceed to VC is equal to 0.88 Newton per millimeter square. Since since V is greater than VC plus 0.4, then provide design links according to ASV over SV is greater or equal to B, this is V minus VC over 0.87 FYV. So which is equal to ASV over SV is equal to B, which is 300, then V is 1.50 minus VC 0.88 over 0.87 times 460. So this one is equal to 0.465. And then select Y8 at 150 millimeter center to center. ASV over SV is equal to 0.671. So this is table 3.13. We proceed to the last item. Now we are done with the deflection. Now we proceed, no, we are done with shear. We now proceed to deflection. So we now proceed to deflection. Which is the last item for today. So the actual deflection, is equal to span over effective depth. So this one is equal to, our span is this one, 8.5, so that is 8,500 over the effective depth, 499. So this one is equal to 17. That one is equal to 17. So by inspection, exterior span is critical when it comes to deflection. It's more important to consider when it comes to deflection. So these are the exterior span, this one, this and this. This one is the interior. So this and this, 3AB and 3CD. These two, they are very important or critical when it comes to deflection. So these are the reason there is no moment resistance at the free end, so sagging is more pronounced, increasing deflection. So in exterior span, in exterior span, there is no moment resistance at the free end. So sagging is more pronounced. Is more pronounced, increasing deflection. So BW over B, so this one is in table 3.12 of BS 8110. So BW over B is equal to 300 over B, which is 1490. Remember, in our previous calculation, or in our previous example, the same question, the same question using the same floor slab for bending, our B was 1490 and our BW, it was 300. So is equal to 0.2, which is less than 0.3. If you check in table 3.12, this principle is applied in that table. So the basic span over effective depth ratio is equal to 20.8. So I will show you the table 3.12. So this is table 3.9 of BS 8110, not 3.12, 3.9. So in this table, as you can see, we have the support condition for continuous, as you can see, for a flanged beam width, as you can see, width of beam over width of the flange less than 0.3. So this is the width of the beam, and this is the width of the flange. And remember, the width of the flange should be less than the condition given is, number one, the actual width, which is the width of the flange itself, and then number two is the web width plus LZ over 5, where LZ is equal to 0.7 times center to center distance of supports. So this is the table. This is the table 3.19. So after calculating this, the actual deflection and the BW over B, which should be less than 0.3, we now proceed to the service stress, which is Fs. So the service stress. So Fs, which is the service stress, is given by this formula: 5/8 Fy, area of steel required, over area of steel provided. So this one is equal to 5/8 times 460 times area of steel required, which is 1878 over 1960. So this 1878, if you check in the first question for bending, you will get you will see this one for span, for this span, for the span that are critical. So span, the exterior span. So 1878 over 1960. So that one is equal to, so this one is equal to 275 Newton per millimeter square. And then the modification factor, which is given by this formula, 0.55 plus 477 minus Fs over 120, 0.9 plus m over bd square. So modification factor is equal to 0.55 plus 477 minus 275 over 120, 0.9 plus m. We'll use m for exterior span, from our previous calculation or question, and it was 365.3 times 10 to power 6, you change from kilonewton meter to Newton millimeter, over B, which is 1490 times 499 square. So this one is equal to 1.45. So this is 356, not 365. 356. So therefore, permissible deflection is equal to basic ratio times modification factor. So this one is equal to 20.8 times 1.45. So this one is equal to 30. So therefore, 30 is greater than 17, which is the actual. Therefore, okay in deflection. So deflection okay. And that marked the end of that question.